In this exercise, we're going to take a look at the functionality built into SolidWorks with their simulation software for finite element analysis. In the basic SolidWorks package, they include something called Simulation Express. And Simulation Express enables you to use some basic functionality for linear analysis within SolidWorks. And you can also import parts made in other systems as well. Today, this exercise, we'll take a look at this little plastic part. It's a bottle opener. At least it's supposed to be a bottle opener. You're given the files, and you're going to go ahead and build it. And from there, then you could go ahead and analyze it. So let us begin. If you take a look in your manual, we're on page 8, you can see some of the things that we're going to have to apply to it and some instructions. But let's begin by looking at the basic drawing here. Now there's two drawings, one with all the fillets and rounds on it, and then there's a kind of a deadened up one, you might say. It doesn't have all the fillets, the external fillets and rounds. As in finite element analysis, generally these things are not necessary, and we could actually construct geometry and analyze it with little or no change to the results. So as we can see here, we have a 2-inch long shaft, and then we're going to go ahead and put in some of these features. So with SolidWorks, we just go to File, New, and we select Part, we hit OK. Once open, the SolidWorks model could have actually materials applied to it automatically. These materials over here on the left-hand side have the ability to transfer on into the SolidWorks simulation software. So why not go ahead and put it in right now. If we look at the specifications on our sheet here, we'll see that's actually the material is going to be nylon. Now there are several different types of nylon, but for simplicity's sake we're just going to stick with what the basic that's given. So we'll right click here and we select Edit Material. And here you could see there's different types of materials to choose from. These are just basic materials. It is possible to go online and actually get materials from manufacturers, for example Bayer or whoever might make some sort of plastic material. You could go in and get all the information needed for that. But in this case, we're just going to go ahead and look under plastics, and there's nylon. We're going to go ahead and select just the nylon 610. And that's pretty much it. But as you can see, there's quite a few different materials in here. And we'll hit apply. Now it's listed in the feature tree. Now we could go ahead and select the front plane of the feature tree, and right away we have the quick launch for sketch. If you don't get that quick launch, it's because you moved away too quickly. Just simply go to the sketch tab up at the top here and find sketch. Now what we can do is we could go in and sketch that geometry. We'll start off at the origin and make sure you select your line tool up here and drag out a line approximately less than a ½ inch high. Click and drag it across, and if you recall, it's about 2 inches, this model of this bottle opener we're making. Click again, drop it down, and you could scroll with the mouse button to zoom up a little closer. Click once you infer to the origin, drag it out, click, and we're going to go ahead and draw a little radius in here. And there's a little trick here to draw on a radius. You could, without going to the tangent arc tool, we could actually go back and tag where we just left off, and it'll automatically create a tangent arc. And now click again, drag this out a little bit further. Again, make sure it's inferring to the other geometry. Click and draw a horizontal line off of that, and then drag this in a bit, drag it across, and right about here give yourself an angle of some sort and infer to the origin and reconnect. Now if you're getting all these little symbols, that's under View, and you turn off Sketch Relations, and then you won't see those. And then hit the green check mark when you're finished. You could hit it 2 times to exit out of the line tool. Alright, now we're going to go ahead and add the dimensions to this. So go to Smart Dimension, click on the top, and just make sure that that line is 2 inches. You might see that this will happen where the geometry actually starts to fall upon itself and maybe twist up a little bit. That's okay. Just keep adding some of the additional dimensions until we get more and more of the geometry done. If this happens where it's actually tying it into a knot you might actually want to hit the undo switch at this point. It might make your life a little bit easier. So you could hit edit, undo, change. And now just simply drag some of this other geometry where you'd like it. And if you zoom up close enough, you'll see that you have the ability to grab and drag these corners and such. Going back to the drawing, so we see that's a 1/2 inch there. We have a 45-degree angle here as well as there. 25-degree angle for the inside where it's going to contact the bottle top, and 3.5 from the center point. So we'll go ahead and continue on with that. And the thickness of this area is 0.25. So let's add that in right now. So from here to here, it's going to be 0.25. This is going to be a 45-degree angle off of this edge, as well as this one will too. Just if you get a message like this, make it driven, that's okay. Just go ahead and hit cancel. We must have actually defined that with other geometry. That's okay. But let's go ahead and define that center point to this point here. This is supposed to be 0.25. Actually, I better go back to the drawing just to double check. Good thing I did, 0.35. Okay. And then this is going to be an angle from here to here of 25 degrees. This radius is going to be 0.125. You'll see it will round it off. That's simply because the tools options is specified in here. It's round to 2 decimal places. If you wanted to see more, you could always go to the tools and options down at the very bottom here, and it will bring up all the different settings, and we'll just simply find under document properties, units, right here we have decimal places, and let's set it to 3 and then hit enter, or hit the OK at the very bottom. And now we can see our 3 decimal places. Alright, as we continue on, we could see we need a 2-inch dimension here, and both of these are 1/2 inch wide across. So this one, actually, we should change that right now while we have a chance. And from here to here, this will be 0.5 as well. And this is going to be 0.2. And that should fully define us. And we know it's fully defined because it actually tells us this at the very bottom, and also because it turns completely black. The geometry, when it's blue, generally is an indication that it's underdefined. Alright, if you hold the middle mouse button, you can see you could rotate it in 3D space. And now we just simply have to extrude it. So we could go to Features, Extrude Boss. And the thickness of this is going to be 0.4. So we go ahead and type in the value here over on the left and hit apply. Alright, you can see there's some transparency associated with the nylon material that we selected. That's alright. We could actually disable that as well, or change this type of view setting, but we could go ahead and stick with that. That's fine. The radii on here, we could actually add them if we want. We could keep a simplified version like this was actually perfect for finite element analysis. Any inside radii generally you do want to keep. Any outside radii, such as what we see here, it's not necessary, these 0.1s. So here's a little trick on what we can do. We could add a configuration. Configurations are similar to other systems. They call them family of parts, and they're variations of a part inside the same part file. And we can find this on this little tab here. If we click on it, and you'll see configurations. There's a default. Let's right click on that, and we could add a configuration, and we could give it a name. We'll call this one FEA. That's the current one we're in. And then we could right click up at the top again where it says part 1 and add another configuration, and we could put in the real, kind of the real world part with the fillets and the rounds on it basically, and details put in. And since we're in the real part and the FEA is already disabled because it's gray, we can see that, might as well try and save this right now. We could go to File, Save, and you'll want to start to save these files in a directory. I'm going to save it on my desktop, and the CAD 208, and since this is exercise 1, call this E1 and put in put FEA on it. Might want to actually put a space between that for exercise 1 FEA, and hit save. Alright, now we could go ahead and add some of those rounds. And as we could see on the actual second sheet, we see a lot more of the details here. So 0.3 is the typical, and then we have some other details, 0.1 on the outer edges. So pretty simple stuff. We'll just go to the fillet tool. 0.1 is going to be on these edges, but let's get in the larger ones first. So 0.3 is going to be this edge here, that edge, and that edge. Hit the green check mark. Go back to fillet, type in 0.1. And this will be, you could select the whole face or individual edges. And actually, I should have probably put some under there as well. Let's see what the print specified. Yeah, they pretty much go on the inside. I forgot the 0.3 over here. So let's add those in just a moment. Actually, we could apply this. This gives us a good opportunity to see how you could modify that by going back to the feature tree and editing fillet 1 by right-clicking on it, and you'll find this edit feature. And we just select the edges that we want to put the 0.3 in. And then actually let's right-click and edit this feature again and just put these in. Okay. Also, there is a little hole in there, so we could select this face here, start our sketch. If we hit the space bar, you'll see a nice option here, normal 2, just double click. You'll also see all the different views you could go to. I'll go normal 2, and we'll take the circle tool, draw a circle in the center here, and if we look at the specifications, that's 0.296 off of the outer edge by 0.2 from the top edge. So we could go over here to the Smart Dimension tool. So from here to here, this is going to be 0.2. And then from the center point to the back edge, this is going to be 0.296. So I was off just by a little bit. Alright, and the diameter is called out at 0.188. Alright, and we'll just cut that through using features, and we have extruded cut. And we'll select through all as an option. And that's pretty much it. Now we could run our analysis, and actually we didn't want to necessarily run it on this part here. We want to run it on our FEA, and sure enough you can see this is the real world part. And let's go to FEA, and we could run it in its simplified mode. This will run faster, more efficiently than the other part, but quite honestly these days with as fast as computers are, you could actually run it in the real mode. The advantage to this is actually just that if you are showing off a simulation to a customer who isn't very well versed with it and how it works, they actually see the real part versus seeing a part that doesn't really look like the part that they had actually worked on, when in reality you do generally want to make a simplified version. But that's okay. We'll go ahead and run our test on here. So now to run the analysis, we could go to Tools, you'll find Cosmos Express, or it's Simulation Express, I believe now, in the latest version of SolidWorks. Click on that. And it might take a moment to load, and it will bring up this information here. And it will give you a welcome and things like that. We'll start off and go through all these tabs one at a time. We'll start over or hit Options. Let's hit Options. Under Options, System of Units. Now, being that we're just starting this, this is our first exercise, we're going to stick with units that we're familiar with in real life. SI is generally the standard, and we'll get into that more and more, but let's go with the inch pound second, which is the English form. And you could let the results default to whatever location you want. You could also put them onto your desktop if you really wanted to. And show annotations for maximum and minimum in the plot results. We could do that. I'm not too concerned about it though. Let's just hit next. Now for the materials, you can see we already specified nylon 610. So if we wanted to, we could specify a different material at this point. Since it's already done, we just go ahead and hit next. But if you did specify a new one, you'd have to hit apply. There's an apply button that usually appears here. Okay, we'll now collect information on restraints. Now this is where you have to give it some thought as to what you're analyzing. And a lot of times if this class is meant not necessarily for engineers, more so it's meant for just designers who might not have the full knowledge of statics and dynamics, but so you might actually need to talk to an engineer in working and figuring out how this is going to be analyzed. But if we think about this, this surface here is going to contact the top surface of our bottle cap. It's pretty much going to stay stationary. This little groove here, or this little edge, is going to snap underneath the edge of the bottle cap. So theoretically we could say that's our fixed face. So, or a restraint. So we'll hit next, and I've already pre-selected it. You can see it puts up little arrows to indicate that's fixed. That's showing the symbol. That's what you see there. So we'll hit next. And we'll, if we wanted to add additional ones, you can. We'll hit next again. Now we could apply force or pressure if we want a concentration of force or a distributed pressure. Well, let's again look at this. Let's flip it around and let me zoom up on it here. Okay, right about here is where your finger is going to be holding it. Your thumb is probably going to be pressing on the back side, on this back edge or the face, and your finger is going to be looped underneath. So right about here is where we're going to go ahead and apply some force, or actually in this case let's apply pressure. Select this face here and hit next, and select pressure. And now we could go ahead and hit next. There's no additional faces that I'm interested in applying to. And how many pounds per square inch do you want to add? Sometimes it's a lot easier to calculate this than not. Sometimes it's very, when you're working with elements that just have a weight to them, you could use the weight and say, oh, that's only going to be 50 pounds of force or pressure that's applied to that area. In this case, it could vary depending upon how strong the person is, honestly, and how tight that bottle cap is on. So just for the sake of this, we'll go ahead and we'll say let's add 300 pounds of pressure. Now you'll see little arrows. The directional arrows are pointing in the direction of the surface that the force is being, or pressure is being applied to. That's fine. If you wanted, you could flip it. There's also other options in the full version of SolidWorks simulation that enable you to actually apply it to a plane or things like that. But we'll go ahead and hit next. We'll just keep it simple here. That's the only one we want to add to, so hit next. And now it's we now have enough information to run the analysis. Do you want to analyze it? Go ahead and make sure yes is selected and hit next. And now hit run. Now it's using a solver. And what it's doing actually, it's first of all, it's meshing it, and that's creating a bunch of little elements, and then it went ahead and it just processed it. Now here we have a factor of safety, and in an engineering course you start to learn about factors of safety. A general one that's non-critical, for example, might be only a factor of safety of 2. That's what you see a lot in industry for things that aren't terribly dangerous. In this case, this isn't something someone's going to hurt themselves terribly, so let's stick with this safety factor of 2. Now, if you're doing something for NASA, you might be requested to have a safety factor of 8 if it's going to go on the space shuttle, for example, because it has to endure tremendous amounts of forces or pressures. And now let's go ahead and just hit Show Me. And this will show us in 2 different shades where if there are any issues. And what we don't want to see generally in a good design, I'll move this out of the way, is we don't want to see a lot of red. In this case, we don't see much, actually. You see a little bit in there. And generally what that's an indication of, as long as it's not going through, you're in good shape. Now this is just a linear analysis. This is not nonlinear. There's 2 different types which are going to be discussed in class. So this is a very simplified analysis. But almost 90% of the engineers use linear. Nonlinear is quite more complex but more realistic in its results. But nonetheless, you could still get some great information in how it's going to fare. In this case, it doesn't look like it's going to fail at all. As long as the red doesn't penetrate all the way through, you're in pretty good shape. There's no failure there. So this actually will work. However, let's go back and modify that a little bit. What if we wanted to add 1,000 pounds of pressure? So we could go ahead and go back here under the load and hit Edit. Hit Next, and we will put 1,000 psi and hit Next and Next. Got to go ahead and run it again. It has to reanalyze it, and it's pretty fast. Okay, and we'll hit Show Me, and we can see there's quite an increase in damage done to this, and interpretation of this really should be left up to like a certified engineer or professional engineer, or actually just an engineer with a degree typically is adequate. But nonetheless, though, you'll find that it varies depending upon how people want to read this. In the past, when I've worked with these things, I've found that if the red goes all the way through, that can be a catastrophic result. In other words, it will break or fail. If there's like a small amount of blue still remaining in there, that's generally a good sign that it's not failing. It's just the surfaces are starting to almost like if you were to take a polyethylene, and if you've ever seen like a plastic, and when you bend it, if it's like a clear plastic and you bend it and you see it turn white on the edges where it's bending, that's somewhat what you might be experiencing or seeing in this case, and it's not a complete failure. And that's where nonlinear analysis comes into play, because as you would realize, the more that bends that bends repetitively, the more it weakens. And linear analysis, which we're doing right now, is only good for really one shot. Nonlinear will give you the results for many shots. So if it keeps bending, how is it going to eventually? It's going to weaken every time, and it's going to be weaker and weaker every time you use it. So that analysis, that's why that analysis is much more thorough. But this is, like I said, most 90% of the engineers out there use this. So let's go ahead and hit Next, and you can optimize the design. We're not going to go ahead and do that today, but we will look at optimization. It will allow you to change the thicknesses to ensure that those loads, it will make suggestions almost what you could change and modify to maybe make it thicker, more durable in the areas that it's about to fail. And so we'll hit No. And then you have different types of results here. You have the displacement, you have the deformed shape. Let's go ahead and we'll just look at the stress distribution, or the von Mises, and we'll talk about this in class. And here you could actually see in a spectrum of color the PSI, or the von Mises, and where there's red, that's of course the higher stress areas. Now what's nice about this is that you could actually animate it. On here there's a save, so you could actually save the animation, or you just hit play. Let's go ahead and hit play, and we could actually see the flexion of the part. Now in this case, what it has a tendency to do, it actually highlights the results by making it more dramatic than it really is. I've actually talked to engineers who's told me in the past that, oh, that's exactly how it would flex. And then if you actually talk to the people who wrote the software, generally they will say, no, that this is augmented to make it very apparent how and what direction it's bending for the engineer to analyze it. So generally you will not see it bend as far as it is. Perhaps with 1,000 psi you might, but not with the 200, 30, or whatever 300 psi that we added initially. So we'll go ahead and hit stop. And that's about it for this exercise. Thank you.